And so what they're doing is they're using the fact that when you apply for a charter school in Boston, you are basically entered into a lottery. And so if you win the lottery or you lose the lottery, is essentially random. It is random. And so we have a really cool treatment control, randomized control trial, like if you were doing a medical study and you were randomly signing some mice to get broccoli and some mice to have snickerdoodles, and which gain more weight, for instance. So this is the same kind of idea where we're randomly assigning students to charter schools and traditional government schools. And so what they find is that the kids that are randomly getting into the charter schools are they do better on their test scores, they do better on their SAT, they take more AP tests, they do better on their AP tests, and they're more likely to enroll in a four-year college, and they're more likely to get scholarships because their test scores are higher. So let me just show you some of the fun figures. Okay, so the red line here is the test scores of all of the kids that won their lottery. So they won the charter school lottery, they got into a charter school lottery. The blue line is the kids that didn't get into the charter school. They were randomly rejected by the lottery. And you can just see that the red line is just a shift to the right, a shift to higher score. So basically all along the distribution, the kids that got into the charter school are doing better in English and language arts. And we really think that English and language arts, like your ability to read and understand material, is probably the most fundamental skill that you can have. It would allow you to learn any other number of skills if you can feel comfortable reading and gleaning information. And then this is for the maths test. And so I think this is really interesting because there's a huge hump in red kind of at these high score levels. And what that means is that just in charter schools, everyone is doing much better. In these non-charter school government type schools, test scores are way more spread out. And in part, that's just because when the school does less, it just depends on what's going on at home, how much parents are spending time with their kids on math. So this is for SAT scores. So you can see here that like the typical SAT score for the charter school winners is like 1330 probably, and the typical score for the charter school losers is like 1150. So that's a pretty big difference actually. And then it's kind of let's see if is it in reading or math, more writing. So there's a difference in reading and math. So actually in reading and math, the difference is about the same. So that's a really cool, and then they're much more likely to go to four-year colleges and much more likely to graduate. So it's a kind of a cool, fun paper. It's I think I will do a lot of work on trying to promote economic mobility, and charter schools are one of these things that seem to really do a lot of good work for low-income kids. Okay, questions. Let me see if I've missed any questions in chat. Routines, teacher, yes. Okay. Any questions from last week? I'm sorry that I canceled class on Thursday. I had a presentation that I was giving in Boston, and just the timing was not was really tight, and I just couldn't handle it. I couldn't do them both at the same time. But the presentation went really well, and so I'm excited about that. Any questions from last week or from your test corrections? Anything like that? Okay, so today we're going to start our final couple weeks. So I guess we have this week and next week, and then the class is over. This has gone really quickly. And this is an important part of econometrics, which is hypothesis testing. And hypothesis testing is just when we have, sorry, I don't know where my marker has gone. There we go. Hypothesis testing is when, say we get, we go out and we do a sample and we think that the average kid at UC Merced is studying 25 hours a week. So we think that the average study time is 25 hours a week. And we do a sample mean, maybe we find that the sample mean is 17 hours per week. And the sample variance is 5 hours a week. So what we're interested in knowing is can we, based on our sample, can we say that this is wrong? Does this imply that this is, so we say, sometimes we say contradiction is like that, so that's wrong. So does our sample imply that this hypothesis is wrong? And we'll talk about how we actually go about doing that. We also will have the same type of idea on our regression coefficient. So remember that sometimes we have a regression coefficient, we're interested in the effect of wages, the effect of education on wages, for instance. So say we had the effect of education was 1 and the standard error on that coefficient was 0.5. So what we'd want to know is this coefficient statistically different than 0? And in this particular example, it would not be different. It would be different than 0 in this particular example. We'll talk about why. Okay. So far in this class, we have focused on computing descriptive statistics and regression equations. And in both of those cases, we often want to know what range of possible realities is consistent with our sample or our regression. And so you'll often hear someone say, oh, there was a positive effect of blank on, IQ. And then someone else will say, yes, but the effect wasn't statistically significant. And all that means is that based on the data, you couldn't tell whether the effect was any different than 0. So if it's something is statistically insignificant, it means that you can't, the result, even if it's positive or negative, is consistent with there being no effect at all. So, so we might say, we might have a question like the following: is the mean wage of the population equal to $12.50 per hour? And then the question is, how confident are we that that is or is not the mean wage? So we'll talk about that from our samples from I think in the next lecture. So today we'll kind of build the machinery that we use to do this, and then tomorrow we'll work on we'll do more of this. And then kind of closer to the regressions that we've been doing more recently, does education have a statistically significant effect on wages, and how confident are we? Okay, so these are really the same kind of thing. And we'll see that that's because of the central limit theorem, which is basically as we take a sample, as we take samples, the samples are randomly, are normally distributed, and they center around the truth. So first, we're going to just start at the very beginning, which is, what is a probability distribution? Probability distribution, we usually describe it as a function like this. A function is a probability density function. And all this does is it describes how likely we are to see each value of x. Okay. So here, say we had this was our function and it makes a line. If we plugged, say this was a function that we could plug in, we could plug in 10 to this function, and it would spit out a number right there. So that looks like, to me, that looks like 0.15. And if you plugged in an 8, that function would spit out a value, something like 0.12. Okay, so it's just a function that describes how likely you are to get each value in the domain. Any questions there or on the previous? Ibrahim, Esmeralda, Devin, Derek, Dennelson, Katrina, Kim. Good so far, no questions? Okay. So so if you think about it, if you added up all of the possibilities, how likely all of the possibilities are, you would get 1. So for instance, say there is a 5% chance I fall on my ass today. There's a 95% chance I don't fall on my ass today. If you add up all of the probabilities of what could happen today, either this happens, I fall, or I don't fall, that's all the possibilities in that space. That will always add up to 1. If my tree could die this year, my tree could die next year, my tree could die the year after that, for the next 50 years until it will certainly die. If I added up all those probabilities, it would add up to 1. So that's just because you can't have more than 100% of all the possibilities. You have exactly 100% of all, if there are all the possibilities available. So one of the interesting things about a probability density function like our f of t is that if we take the integral of f of t along all the domain, so if we measure the space under any density function, it's always 1. And all that expresses the intuition that I was just saying, which is if you add up all the probabilities of everything that could happen around a particular event, you sum it to 1. So another good example is dice. I'm going to roll the dice 1 time. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. If I add up the probability of rolling each of those, I will get 1. Any questions on that? That's a kind of a foundational thing for everything. Will we do actual integration, or will we be using trapezoidal estimation to calculate the area under the curve only? We will not be doing very much integration. We won't do any integration that's hard. We will be, I'll show you one way to integrate a simple distribution, and it's so simple, it will be totally obvious to you. One of the interesting things is that often when we're using a t-test, which you've seen before in your statistics class and you'll see again today, you're implicitly doing an integration, or the table is doing the integration for you. So, but there won't be any difficult calculus related to this. Okay, so what that means is if you took the integral between any 2 numbers c and d, you would be finding the probability that the x's that you draw would be between those 2 numbers. So remember, when you integrate the whole thing, it will be 1, which is 100%. When you take the integral between any 2 values, it will be the probability that you draw a number between those 2 values. Okay. Related is that if you wanted to know whether a number, so say that these are times from a mile run, perhaps. You wanted to know what's the probability that a person from the sample will have a time greater than 8 minutes. You could integrate the density function from 8 to infinity. I'll give you this. So you get, when you integrate, you get, okay, there's like a 20, probably like something like a 25% chance that that a random person in the data has a mile time larger than 8 minutes. And the integral, remember, is just the area under the curve. So if it's been a minute since you've taken calculus, let me just write what an integral is. An integral is the area under a curve. The total area under a probability density function will always be 1. And then the area in any region will be less than 1. And it will be the probability of drawing a value in that region. Okay, let me stop for questions there. Yesenia, Warren, Stephanie, Saul, Noah, Manuel. Okay. Thumbs up. Sounds good. Okay, so there are two challenges. One is that we often don't know what the density function is. It's very hard to find a function that exactly represents what a data generating process looks like. And even if we know it, it's often really difficult to integrate. So integration is a really challenging calculus problem, and often we don't do it because it's so challenging. We find ways around it, ways around integrating. So there are two exceptions to that, which we've seen before. There's the uniform distribution. And remember, the uniform distribution is when the data, when getting different events, all has the same probability. So remember, when we were rolling dice, no matter what number it is that we're rolling, you have a 16.6 chance of rolling that number. So these are intended to be approximately even. The second is a normal distribution. It's nice because it occurs frequently in nature and it's symmetrical, so that makes integration much easier as well. And remember, normal distribution is any place where the data are symmetrical. There's a heap in the middle and thin tails on the edges. That's a normal distribution. Normal just means that there's a bunch of people in the middle, a bunch of firms or animals or whomever. So this is the uniform distribution is just nice because it helps us kind of generate intuition. So uniform distribution has an equal probability between A and B, where A is the minimum value of the uniform distribution and B is the maximum value of the uniform distribution. So when we were rolling a dice, B would be 6 and A would be 1. So say we had the same examples we had before, where it's your mile run time. If we wanted to know the probability of the probability of any time is going to be actually the same because it's uniform. So we're just going to use this function. It's going to be 1 over 14, which is the maximum, minus 4. And that will give us 1 over 10, or 10%. Okay, so what does that mean? It means basically, what's the odds of having a 6-minute mile on the data? 10%. What's the odds of having a 12-minute mile on the data? 10%. What's the odds of having a 5-minute mile on the data? 10%. It just means no matter what t you plug in there, it's a constant. The probability is a constant. Any questions here? If we want to know the probability of x falling between C and D, we integrate over the range. So we had, this is a really easy formula. I'll just show it to you. So remember, this is the probability density function, and we're integrating it from C to D. So because this is a constant, we can pull it out of the integral. That's where this comes from. So we're just taking the integral of 1 from C to D, which is x evaluated from C to D, times this just keeps carrying down. And when we evaluate x from C to D, it's just going to be D minus C over B minus A. So let's do a quick example over that. And that will be the probability of getting an x within a range of values from C to D. Okay, so here we want to know whether we will draw someone that has a mile time between 11 minutes and 14 minutes. So our formula was D minus C over B minus A. Okay, so that's just going to be 14 minus 11 divided by 14 minus 4, which is going to be 3 on the top and 10 on the bottom. So that's just 30%. Okay, so there's a 30% chance we draw someone that has between an 11 and a 14-minute mile. Okay, the standard normal distribution has a mean of 0 and a standard deviation of 1. So that's just a feature of the standard normal distribution. It's very nice because it's always centered on 0, and the standard deviation is always 1. So what is the variance of a distribution whose standard deviation is 1? Luis, Leana, Kimberly, Katrina, Abraham. What's the variance of a variable whose standard deviation is 1? Anyone know? Yep, it's 1. It's just, remember, the variance is just the square of the standard deviation. So one fun thing about the standard normal is that the variance and the standard deviation are the same. Okay, but many times we do not have, our variable is not a standard normal. So sometimes we have a normal distribution, but not a standard normal distribution. Oh, so this is typically actually one of the things that we're doing here. We would like to know the probability that x falls more than 2 standard deviations above 0. So typically when we say something is statistically significant, what we mean is that the variable is 2 standard deviations or greater farther from what we thought it would be. That's a statistically significant difference. So we're usually interested in what is how likely is it to have a value above 2. And so what is this? This is the probability. If you integrated that, that's the probability of getting a value larger than 2 standard deviations. So usually this is a small probability This is usually 2.5%. The probability of getting above 2.2 standard deviations away. Okay. The standard normal distribution has a complicated density function that's really quite difficult to integrate. So I don't know if you've ever had a calculus class and you're given a test where like they say, integrate this. And you're like, oh no, the x is in the exponent of e and it has its own exponent. I mean, actually, I don't know how. I think this isn't that hard, but it definitely looks difficult. But what we do instead is we use a table of all the integral values that we need for the standard normal distribution using a t table. So let me just show you one of these really quick. So this is, I would usually just go t table. And I always like this one with the blue stripes. Okay, so let me just walk you through this a little bit. So on the left-hand column, these 11, 13, 14, 15, etc., are the data size. And typically, actually, we don't really use any row but the bottom row. So this row where it says Z, this row where it says Z is usually the row that we look at because we're usually dealing with samples that are larger than 1,000. If you had a sample that was 20, though, you would go to this row where the sample is 20. You would look across that way. Okay. But in practice, like a person who is using statistics for their livelihood would usually be using this bottom row because their data would be big enough. Okay. So then what we have is the confidence levels are along the bottom. So say we got a standard normal when we calculated the t-test, which I'll show you in a second, we got 1.036. We'd say, how confident are we that that this is consistent with the null hypothesis, which I'll show you in a minute. And what we'd say is, well, we're about 70% confident that this is consistent with the value, the null hypothesis. I'm sorry, I'm missing this a little bit. I think it would be, we're 30%, it's 30% possible to get that and then actually be the same. So then what we are usually looking for are high confidence values. So if we get a t-statistic that's 3.5, we are very confident that the null hypothesis is statistically different than the sample value that we've got. So let me stop and take questions there. I think that many of you have seen these tables before. You probably used them in high school, maybe even middle school, and maybe probably hopefully in stats before this class. I actually don't even know that I don't think I put this on the test, but this is just very kind of fundamental part of statistics. So normally, actually, what we're usually looking for, kind of one of the big benchmarks, is the 95% confidence interval. So that 1.96 is the number of standard deviations away from the mean you need to have to have a 5% confidence that these are different, or 95% confidence that they're the same. Let me see here. Ibra, in high school, we were taught how to find the z-score on the calculator. Yeah, we'll do the z-score. We'll do z-scores together with the t-stats. Okay. Okay. So we can do this together actually based on the things that we just talked about. So say we have, okay, so we have this random distribution called X, and we can, it's like a dice, but it's a dice with a billion sides, and some of those sides are more likely to show than others. Okay, so it's a random draw, but there are some values that are more likely to come up than others, and there are tons and tons of values. There's not just six. There's billions of values we can roll on this dice. Okay, so what's the probability that a random draw is greater than 1.96? Well, from that table, we said that that was the 5%. That's the threshold for 5% confidence. 5%. That's the 5% confidence threshold. And because it's a two-tailed test, there is 1/2 of that. So two-tailed means that we want to know about extreme values in both tails. So instead of 5% at one end, what we actually want is 2.5% at each end. That's the 5% significant. So what is the likelihood of getting a value that's greater than 1.96? It's 5% divided by 2, which is 2.5%. Questions there? Katrina, Kimberly, Leanna, Luis, Manuel, Noah? Okay.
Pardon, Professor?
Yeah.
What'd you say?
Oh, I just said, did you have any questions?
No, I'm doing fine. I was just writing notes.
Sounds good. Okay, so this is a good one. So I've just asked, what's the likelihood that you get a number larger than 1.96? The next question is, what's the probability of getting a draw less than negative 1.96? Can anyone think about this out loud? Does anyone have an idea? So one helpful thing is that the normal distribution is symmetric at 0. Exactly. So if there's a 2.5 probability that you get above a 1.96, there's an equal probability that you get less than negative 1.96. So that's just because, and Abraham, that was perfect. Thank you. So say we have, it's always centered at 0. We have a distribution like this. So say we knew the probability of this, we would also know that the probability of the thing that's exactly the opposite on the other side is the same. So that's also 2.5%. Okay, so this is a fun one. So we've got a normal distribution. And what we want to know is what's the probability between here and there, where we already know the probability between 1.96 and infinity is 2.5%. And we know that 1/2 of the distribution is 0.5. Okay, so to find what is the odds of drawing someone a number between 0 and 1.96 is going to be 0.5 minus 0.025, or 0.475, so 47.5%. Okay. Questions there? Okay, and then this last one, we saw that the threshold for 70, so usually we want the 95% confidence interval. The 70% confidence interval is this right here. So if we had a value that was just higher than 1.036, we would say that there's a significant at the 30% level, which is actually not significant at all. So what's the probability that we have a random draw within 1.036 of 0? We would say we have a 70% chance of drawing between negative 1.036 and positive 1.036. Questions on any of those? Okay. Let's take a break. Let's take a little break. I'm going to, question. Can you show how you got 70? Yes. Let me do that before we have a break. Okay, so remember we had these t-tables, and I went down here and we were looking for, the value is 1.036. The confidence interval for a t-statistic of 1.036 is 70. And all that means is that the probability of drawing a number in a standard normal distribution that's between negative 1.036 and positive 1.036 is 70%. That's actually what the confidence interval means. Those are given depending on the other percentages two, right? Those are given depending on the other percentages too, right? Yeah. I think so. Yeah, those depend on what other percentages are you thinking about?
Because those percentage intervals vary to the top and bottom.
Sorry, say it one more time.
Intervals vary to the top.
Sorry, just a second. I'm getting an echo. Okay, sorry. Would you state it? Just one second. Yep. Can you hear me, Noah? Okay. Let's vary to the top and bottom. Oh, yes. You're saying that this 70% applies to all of these as well, right? Is that right? Okay, perfect. That's true. That's true. That's true. Awesome. Perfect. Other question? Oh, and does that answer the question about? Does that answer the question about how we got 70% here? Does that answer that question? Awesome. Okay. Cool. Let's take a little break. I'll show you something hilarious. Help. Okay. Okay, can I just ask, can you hear the video? Can you guys hear the video? No? Okay. Do this real quick. Okay.
To the Sun newspaper. I'll just read it to you. Right.
Can you hear this? You want to hear that?
I was recently walking. I have been trying to sell fake stories to newspapers. And this is one I tried to sell to the Sun newspaper. I'll just read it to you. Right. I was recently walking through London Soho when I spotted Matt Baker from the BBC One show on his phone in the street. He seemed angry about something, and at one point he was so angry that, to my amazement, he tried to kick a pigeon. He had about 3 attempts, and on one of them he did clip its wing. He was shouting what sounded like, "Die, pigeon prick." Anyway, I've never met that baker. I managed to get some pictures. I was wondering how much you might be interested in buying them for. I got a reply from the Sun newspaper within 2 minutes. They said, "Joe, kicking a pigeon, question mark. That is pretty shitty for a one-show bloke." Colloquial for a first email back, I feel. Can you send me the pictures? Cheers. I can't give his real name for legal reasons, so I'll call him Rodney. That's it. Rodney, my lawyer says I shouldn't send you the full pictures until I have an offer from you as to how much you'll pay for them. I've attached a cropped version of one of the shots for the time being. Response? He replied, "That's a photo of a pigeon." Stoops. Here's my photo of a pigeon. He attached that one on the top there. He also attached a picture of Matt Baker and said, "Can you send me a picture of this man kicking a pigeon?" So I sent him a curveball and I just said, "Is that a picture of Matt Baker? I thought he was Chinese." You thought he was Chinese, question mark. You mean you have a picture of a Chinese man kicking a pigeon? I said, "Yes, how much will you pay for it?" I said, "I fear we might be wasting each other's time. Good day." You'll be sorry when you see tomorrow's Guardian front page. Good day. So I spent.
Anyway, I'll show you a couple more of him later, but I think he's so funny. Okay. I'm going to grab a snack and go to the restroom. Feel free to take a small break. Awesome. Okay. Okay, any questions? Any questions settle on you? Let's see. I'm trying to, I have like a little echo. I'm trying to figure out where it's coming from. Where? There it is. Okay. It's probably better this way, actually. Okay. So this is student t's distribution. Between 0 and 1 is this inner area. Do you remember when we talked about this? I think it was part of our slide deck before, and we said, how likely are you to be within 1 standard deviation of the mean? And we had 60.
So we can't see your screen.
Oh, yes, of course, sorry. I thought maybe you could just imagine what I was doing. That'd be okay. Thank you for letting me know. I would have gone on for a long time and never noticed. So remember, we had in our old slides, we had what are the odds of being within 1 standard deviation of the mean? It was 68%. In this example that we just did, it was how likely are you to be within 1.036 standard deviations of the mean, and that's just obviously slightly less than 70% because 1 is slightly less than 1.036. Okay. Okay, so many distributions are normal, but they're usually not standard normal. They usually don't have a mean of 0 and a standard deviation of 1. And so it's actually quite easy to take any normal distribution and just adjust it so that it becomes a standard normal distribution. All you do is you subtract the mean of the data and you divide it by the standard deviation, and that will make any normal variable x into a standard normal with a mean of 0 and a standard deviation of 1. All you're doing is dividing it so it's in smaller units, so that the standard deviation is 1, and you're subtracting off the mean. So say it's say it's over here. Say you've got, here's 0. You've got this distribution over here with a larger standard deviation, and it doesn't have a mean of 0. Well, if we just subtract the mean and divide it by the standard deviation, we'll get something like this. So it will now have its center over 0, and its standard deviation will be 1. Okay. That's what we do here. This is another example. We have some distribution with a mean of mu that's not 0 and a standard deviation of a sigma x. And we're just going to subtract from each variable in x the mu, and then divide by the standard deviation. And that will give us back our standard normal variable, our standard normal distribution. So that's just kind of great. We can always get back to this place where we kind of know what's going on. Okay. So we're specifically interested in testing hypotheses about usually 2 things. One is the sample mean. So we want to know how many hours UC Merced students teach. We want to know the body mass index of students, so we know kind of where are there lots of anorexic bulimic people, are there lots of obese people. Maybe we're interested in knowing how severe the health problems are. So sometimes useful to just know what the distribution looks like. So luckily for us, sample means and regression coefficients both have normal distributions. They have a mean that is over the truth, and they're normally, if you kept sampling and re-estimating them, those betas or those sample means would have a normal distribution over the truth. So said very precisely, The sample means are normally distributed around the true population mean because of the central limit theorem. And then in the exact same way for regression coefficients, if you were to resample the data and re-estimate beta 1 over and over and over again, those beta 1s would also be normally distributed around the true population value beta 1, and the regression errors would be normally distributed. So what that means is that we can, for both when we're interested in understanding the sample mean, and when we're interested in understanding whether a beta, a coefficient, is statistically significant, we're able to use t-tests for both of those. Okay, so the null hypothesis is usually, we think that the sample is, we think that students on average are studying for 25 hours a week. Not too much and not a ton. So if C is the true population mean, then the sample mean will be tightly clustered around that mean. If we have a sample mean that is far away from C, however, and has a low probability of occurring in the data, then we think that C is not actually the true mean, and we reject our null hypothesis. So what that is, said another way, is that to begin with, we start with the hypothesis. We say, we're going to have it's almost like making a guess. We don't really do this very often, but we make a guess and we say, we think that the sample mean is 25. And then we go out and we sample the world and we find out what the sample mean is. And we either find a sample mean that's kind of close, or we find a sample mean that's far. And if it's sufficiently far, then we reject our hypothesis. We say our hypothesis was wrong. It's not true that the average UC Merced student is studying 25 hours a week. They're studying more like 15 hours a week. So if we have a sample mean that's close to C and has a high probability of occurring, then we think that C could be true, and we don't reject the null hypothesis. So it's not that we know that the null hypothesis is exactly true, but we just don't have data that conflict with the null hypothesis. Questions there? This is a really kind of also a nice, important fundamental part of this arc. So say we have some null hypothesis that X bar is equal to C. And we have, to calculate our t statistic, all we do is we turn this into a standard normal distribution, essentially. We take our sample mean, subtract off our null hypothesis value, and divide by the standard error of our sample, our data. We look at the t-table and we find the critical number of standard errors, t critical, away from C we need to be in order to be statistically different than C at the desired level, which is usually the 95% level. So we'll do an example of this together. If the magnitude of the t-statistic exceeds the critical value, then we reject the null hypothesis that the sample mean is equal to C. If it doesn't, then we don't reject that they're equal. So it's just if we don't reject they're equal, the data are consistent with the null hypothesis. Okay. Any questions there? We'll do an example in a minute. Kimberly, Daniel, Derek, Danielson, Devin, Esmeralda, Abraham. Sorry, the baby was crying. Okay, if we want to reject the 95% confidence level, then we want there to be a 2.5% chance of having a t-statistic at least as large as our critical value. Let me see. Got some chat. No question, no question. I can't see. Okay, so here's a good example. We're going to hypothesize that the average UC Merced student studies 5 hours a day. And we randomly sample 100 students and compute the mean number of hours and the standard error of the mean. So 5 hours a day, we think. Okay. So when we get our sample, we're going to calculate the sample mean of how many hours they study, and say we'll calculate that in this sample that we get 4.3 hours a day is the average that they study per day in our data set. And we'll get the estimated standard deviation of the mean is 0.03. I'm sorry, 0.3, just 0.3, sorry. Point 0.3 is hours per day. Okay. So one important thing is that when we're calculating, this is not exactly the same as the standard error in the data. So when we're calculating the standard error of the sample mean, we're going to take 1 over the square root of n and multiply it by the standard error of the data. So if we would have a standard error in the data of 3, and to find the standard error of the sample means, we have to adjust it by 1 over the square root of n. And so what do we get here? We are going to do a generated t-statistic, which is, we're going to take 4.3. I usually do it the other way around. Usually do the larger value first. 5 minus 4.3 divided by 0.3. Remember, it's because we're doing the sample mean minus the null hypothesis divided by the standard error of the sample means. So what we're going to get is 0.7 divided by 0.3, which is going to be 2.333. Okay. So this, if we went back and looked at our table, remember that our critical value for the 95% confidence was 1.96. And since 2.33333 is larger than 1.96, we're going to say that these are different at the 95% confidence level. Okay. Questions there? This is an important thing. I'm guessing a lot of you have seen this before, but it's really important. And Yesenia, Warren, Stephanie, Noah, Manuel, Luis, Leana. Okay, sounds good. So let's just go over those steps really quick one more time because it's so important. So we're going to compute the t-statistic. We're going to use our t-statistic formula, which is that the sample mean minus the null hypothesis value divided by the standard deviation of the sample means. We plugged in our values here, and we got a number, negative or positive 2.33. It's totally, those are the same. Those are isomorphic. It's 2.33 away from the mean, regardless of whether it's above or below, it's the same. And then we looked up the T critical value at the 95% level, and that was 1.98. And we reject the null hypothesis based on that. So we said with 95% confidence, students are not studying 5 hours a week. They're studying something more close to 4.3. Questions there? So there's less than a 5% chance that the sample mean would fall this many standard errors away from the true mean. So we're getting a value, remember out here, that's like negative 2.33. And you can just see it's pretty unlikely that we'd be getting that value by chance. If really students were studying 5 hours a week, it'd be very unlikely to get value 2.33 standard deviations away from 5 if they were really studying 5. So it just means that our null hypothesis was probably wrong. 5 is too high of a number for that for our sample. Our sample suggests it's something lower than 5. Okay, so the UC Merced deans would like the average GPA to be a 3.0, and they pull random 42 students and find that the average GPA of these students is 3.15. They find that the standard error of this mean is 0.12. Can we reject that the true average is 3.0 at the 90% confidence level? So what's our null hypothesis? Our null is that I'm going to just write the average of GPA is equal to 3.0. Step 1 is, what is our step 1? We're going to calculate the T statistic. T will be equal to, remember, G prime minus SC. No, I'm sorry. I'm going to redo my my notation. So I'm sorry. I'm going to say that the average GPA, the null hypothesis is that C is equal, the real true GPA is equal to 3.0. We're going to go out and calculate from a new sample of 42 students what the average GPA is. And we're going to divide that difference by the estimated standard error of the means, of the sample means. And so what do we get? We're going to have 3.15 minus 3.00 divided by 0.12. So we're going to get 0.15 divided by 0.12. That is going to be 1.32 1.3 divided by 12 is 1/4. Yeah, so that's true. Then we're going to go and look up what the critical value is for the 90% confidence place. So we're going back to our table. I'm going to look for 90% confidence, and I'm going to go up to where, because we have 42 students. So I'm going to just use 40, and I'm going to see here is 1.684. 1.684. So that's our critical value. Critical value is 1.684. Crit 1.684. And so we're not getting a T statistic that's greater than the critical value. So therefore, we don't reject the null hypothesis. So what does that mean? It just means that our sample is consistent with the null hypothesis that the average GPA is actually 3.0. So why is that? Sometimes you'll pick 42 students and you'll even if the true average GPA is 3.0, if you take a random 42 students, you might pick, on accident, you might pick a bunch of great students. And you'll have a GPA slightly higher than 3. You might accidentally, by random, pick a bunch of crummy students and get a 2.7 or something like that. So that's all possible, even if you're randomly selecting. But it's not very likely as the sample gets large that you get an unrepresentative sample. So questions here, questions on this?
Can you show again how you got 1.684?
Sure, yeah. So we have from the question that we want to know if we can reject at the 90% confidence interval. So all I'm taking from the question is this 90%. And I'm going to, and actually one other thing, let me show you. The other thing I'm taking is that we have 42 students in our sample. So our sample size is 42 and our confidence level that we want to test at is at the 90% level. So then when I go to the table, I'm going to basically try to find the intersection of this column where that's 90% is the confidence level, and this row where 40 is the sample size. So they intersect right here at 1.684. What does that mean? That just means that that is our critical value. If we get a value, a t-statistic that's larger than that in absolute value, then we can reject the null with a 90% confidence. Does that click a little bit?
Yeah, thank you.
Awesome. Okay. Other questions here? So we're not going to worry about stata. Yeah, we're not going to worry about stata. So that is all for today. I had a homework plan, but we just won't have time to get into it today. But we will come back tomorrow and we will get into the next slide deck 10. And yeah, I will hang back and answer questions if you have any. Make sure you turn in your resume tonight. That's really easy points. And yeah, class dismissed. Great to see you all. You too there. Thanks, Esmeralda. Thanks, Kim. Thanks, Yesenia, Leanna.
So, Professor,
Yeah.
if we know how to like do this all on a calculator, are we allowed to? Or?
Yeah, you can use your calculator. Yeah.
All right, for sure. Thank you.
Yeah, of course.
Have a good day.
You too.